Hello and welcome to this lecture. In this lecture, we'll start by quickly seeing how we can compute eigenvalues, eigenvectors by computer. I'm going to show you a MATLAB illustration and we'll quickly see a few problems in this general area of eigenvalues, computation, properties and all of that. I may not solve all the problems in great detail, we'll just show you the brief idea. Okay. So, the main function that is used in MATLAB for computing eigenvalues is called this EIG. Okay. So, you can do EIG of a matrix. It's supposed to give you two things, right? It's supposed to give you V and D. Okay. D is a diagonal matrix. It will put out the values in a diagonal form. Diagonal matrix, so notice here D is a diagonal matrix. It has the eigenvalues. Okay. It's returned as a matrix. It could be returned as a vector as well. V is the right eigenvectors. Okay. So, and W is the left eigenvectors. I told you about the left eigenvectors also, right. So, you can return 3 values from EIG, 2 values from EIG or 1 value. If you return 1 value, it will only give you the eigenvalues. If you return 2, it will give you the eigenvalues as a diagonal matrix and a vector of eigenvectors and so on. Okay. So, how it uses it and all, you can see, it has its own algorithms. You can talk about generalized eigenvalue algorithm, what do they do, Cholesky or QZ or something, some such method is used. Okay. So, let's see it in operation. And in operation, I think it's good to use symbolic matrices because symbolic matrices are nice to do. So, here is a symbolic matrix. So, let's just do one. I think I gave you this example 0, 1, 0. This should be fairly stable. It should get something. Okay. So, this is my A. Okay. And then I can do EIG of A. Okay. So, it gave you the answer 0, 1, 2. Maybe this is something you did. You can also get the eigenvectors if you want V comma D equals. So, notice it gives you 0, 1 D on the diagonal and you gave you minus 1, 0, 0, 1, 0, 1, 0, 1. So, you can pick any other thing. So, let's pick something more random. Let's just see, we do some 1, 2, 1 here, 0, 1, 1 here and then 1, 1, 1. Why not, right? So, leave it like that and then ask it for EIG. Ooh, look at that. Okay. So, I think so it gave you a complicated thing and it looks like it's some complex number also. And if you want it to compute, you can use this something called VPA, which is like a numerical computation. So, it does a numerical computation and gives you. So, it will give you as a radical this symbolic toolbox is like that. It gives you in radical form, but you can compute numerically and you can see it's got one real eigenvalue and a complex conjugate pair of eigenvalues. So, remember, if you have a polynomial of degree 3 and real coefficients, you should have one real root and the other roots will be complex conjugate pair, right. So, that is what is going on here. So, you got the answer. Okay. So, you can change this matrix and you will get it. So, if you want to know the eigenvalues, eigenvectors, you have to call it in this V comma D form. Okay, I made a mess here, V comma D. So, we do not want to see the whole gory detail of what V comma D will look like. So, you can do this VPA stuff, VPA will just evaluate it. And so, you notice here we have got 3 eigenvectors. The first eigenvector is real, that corresponds to the eigenvalue of this 2.76 guy. The next two guys are conjugates of each other. So, you can see they are conjugates of each other. First, this one will correspond to the second eigenvalue and the last one will correspond to this case. So, we saw that they have to be in conjugate form. That also is a property that we see. Okay, so, it is very simple to do this computation. So, you can also do some interesting ones. I think MATLAB has some examples. So, this is a wonderful example, gallery of 5. So, let us just say, let us just ask for A equals gallery of 5. Gallery is like some built-in matrices of some special types. So, you will see one interesting property here. So, let us just do V comma D equals EIG of A. Ooh, it looks a little ugly, but anyway, we got the answer we wanted, I think. So, the diagonal values will give you the eigen values. Okay. So, anyway, so I think this is something. So, you get the diagonal values here. It's got one real eigenvalue and then 2 complex conjugate pairs, and the eigenvectors are along the columns, and you get this, right. So maybe if I do sim, I think that will also be different. So in this case, I just got numerical value. You can also do sim, I think, and then do it. Okay. So you can pick up many matrices like this and come up with examples. So I don't know if gallery of 1 is, what happens? Invalid n, it doesn't like n. Okay. Gallery of 2. Okay. 5 is okay, it likes 5, I don't know why. Maybe I should look at help gallery. Okay, test matrices. So it has a bunch of things. So I guess I can't give random things. You can say matrix name is binomial. It has a whole bunch of things and some input parameters, and all the 3 and 5 are possible, right? So okay, so let's look at gallery of 3. Is it an interesting thing? 5 I thought was a bit interesting, but it's not doing that. So let's do A equals sim of gallery of 3. Maybe it will be a bit more interesting, I don't know. So let's look at eigenvalue of A. Oh, 1, 2, 3, look at that, became very, very interesting. So V comma D, we can say Eig of A, maybe it will be a bit interesting. So yeah, this is quite nice, it's got rational form. 3, 1, 2, and 3 has got this eigenvector, 1 has got this eigenvector, 2 has got this eigenvector. So anyway, so I think you may ask very correctly, why should you even bother with learning all the by hand methods? So quite often, sometimes in applications, you have to make judgments on what happens to eigenvectors when the matrix changes a bit, this, that, and all that. So you can't keep computing every time. You should have some intuition on how the eigenvalues behave as well. So it's good to know the properties. It's also good to know the computing tool which will evaluate this for you. Okay. Okay, so let's move on to this guy and then go to some of the problems I have in this thing. So I picked up a few problems which I thought is a bit interesting. Some of them I'll try to give you a brief idea. I'm not going to solve it in great detail. You can try it on your own. You have to try these problems. Only when you solve problems, you really pick up the ideas behind the topic. Okay, so here is a matrix A. It's got an eigenvector u with eigenvalue 1 and an eigenvector v with eigenvalue 2. Okay, so you got to find possible eigenvalues, eigenvector pairs for this matrix A squared plus 3a plus 2i. Remember I told you, so if you have an algebraic combination like this, and if you know the eigenvectors for A, you can just see what happens when you multiply this with u, right? So when you multiply this with u, you're going to get lambda squared u, eigenvalue squared u plus 3 times eigenvalue u plus 2 times u itself. So u comes out. So you see that the square, so if you put, instead of a, if you put 1, you will get the answer. So 1 plus 3 plus 2, you will have an eigenvalue 5 or 6 with eigenvector as u. If you put in v, you have to put 2 here. So you will get 4 plus 6, 10 plus 2, 12. So 12 with eigenvector v and 6 with eigenvector u. Okay, so that's how it goes. So you can see how I evaluated it. Not writing it in great detail. If you write it down, you will see that that will work out. Okay. So here's another interesting little question. Supposing you have a non-zero matrix A, but it satisfies A cube equals 0. Okay. So what are the possible eigenvalues of A? It's asked. Okay. Wow. Seems like an interesting question, right? So if A has an eigenvalue lambda, A cube is going to have an eigenvalue of lambda power 3. But A cube is 0. Okay. So we've seen cases where this may happen. So which means any possible eigenvalue for lambda for A has to be equal to 0, right? You can never have a non-zero eigenvalue. Okay. So lambda is going to be 0. So all the eigenvalues of A have to be 0. So 0 has to be the only eigenvalue of A. Okay. But A is a non-zero matrix, which means its nullity will never be n. Okay. So the 0 eigenvalue will have algebraic multiplicity of n, but its geometric multiplicity will be strictly less than n. Okay. So you can say that the only eigenvalue for A is 0, but its GM is strictly less than its AM because A is non-zero. Okay. So that's a interesting relationship. This is what I meant by saying why should you know about properties of eigenvalues, eigenvectors. Given some conditions and situation, you should be able to figure out what can happen with eigenvalues and eigenvectors. Okay, so here is a problem. I'm not going to solve it fully again. I'll expect you to solve it. But what are the possibilities, right? So this is a 4 by 4 matrix. You may think numerically it's a bit of a pain. Yes, if you do it by hand, it is a bit of a pain. But maybe you can say something here about what can be eigenvalues, eigenvectors by inspection without doing a lot of work. If you look at the first matrix, if you notice, the 0, 1, 0, 0 is occurring at the second position. So the 0, 1, 0, 0 itself will be an eigenvector for this matrix with eigenvalue 1. So you can quickly figure that out. So there's an eigenvalue 1 and 0, 1, 0, 0. Another thing you quickly notice is the first column and the last column are identical. So it's got a nullity here, right? So it's got a null space vector 1, 0, 0, minus 1, and that is also going to be an eigenvector with eigenvalue 0. So you've already found out 2 eigenvectors and 2 eigenvalues, okay? And then if you now write this, you already know 2 and you can figure out other things, okay? So I'll expect you to work that out on your own, okay? So let's come back to this example B. This example B, the curious point is that every row sum is 6, right? Every row sums to 6, right? So you've got all ones being an eigenvector with eigenvalue 6, okay? That's the first observation. Second observation is first row and the fourth row are identical, which means it's again singular. So there will be a null space vector. So you find that null space vector, you will get that eigenvector with eigenvalue 0. So you can identify an eigenvalue 0 with an eigenvector, identify an eigenvalue 6 with an eigenvector, and then if you try and do some determinant type stuff, you will get the remainder, okay? So these are some things which you can do. So when you have a matrix like this, of course you can do the calculation or give it to MATLAB and find everything, but then intuitively you may be able to figure out some of the interesting properties, okay? So here is another one, interesting little problem. It looks a little wrong. So you have an 3 by 3 invertible matrix A, and it's got eigenvalues 1, 2, 3, and there are eigenvectors 0, 1, 0, 0, 0, 1, 1, 0, 0, 1. What are the eigenvalues and eigenvectors of the matrices A inverse? So A inverse has the same eigenvectors, but with eigenvalues 1 by this. So it's 1, 1 by 2, 1 by 3 with corresponding eigenvectors this. What about SA S inverse? The eigenvalues are the same, but eigenvectors you have to multiply by S. So it becomes S times 1, 1, 0, S times 1, 0, 1, 1, S times 0, 0, 1. Okay. So those will be the eigenvalues and eigenvectors of SA S inverse. Okay. So I hope this is clear. So this is the fourth question. The last question is a little bit of a challenge question. You can think about it. It's interesting. I'll give you one answer, but maybe the last part is a bit interesting. Okay. So you find 5 by 5 matrices A1 to A5. Okay, you have to find 5 by 5 matrices, 5 of them, everything is 5, right? So which all have a single eigenvalue 0 with algebraic multiplicity 5. Okay, so they should only have an eigenvalue 0. There's nothing else they should have. But I want the geometric multiplicity of AI to be I, as in geometric multiplicity of 0 for A1 should be 1, geometric multiplicity for A5 should be 5, geometric multiplicity for A4 should be 4, etc. Okay. So how do you approach this? So first of all, easy examples like this you can always construct with triangular matrices. Keep that in mind. So for most eigenvalue examples, if somebody wants you to construct a matrix to show an extreme eigenvalue property, it's enough if you do triangular. Okay, so this may sound surprising to you. We'll see a result later on, maybe, which will convince you that that's true. It's enough if you do triangular. You don't have to go beyond triangular for examples. In fact, it's enough if you do triangular and one other diagonal. Okay, so that's a little bit more tricky, but triangle is all that you need. You don't need anything more for eigenvalue examples. So think triangular, right? So if you think triangular, you want only an eigenvalue 0 with algebraic multiplicity 5, which means what? Lower triangular, let's say, all the diagonal elements are 0, right? So you've got 0, 0, 0, 0, 0. Okay. Now when will you have geometric multiplicity of 5? That's only possible when the entire matrix is 0, no? You need 5 null space vectors, nullity has to be 5, so rank has to be 0, which means all 0 vector. What about geometric multiplicity of 4? I want nullity of 4, which means rank has to be 1. So you pick any rank 1 matrix, right? So you just pick all 0 on the diagonal and then put one value on the lower triangular part to make rank 1. Just put one value somewhere, you'll get rank 1, right? So that's all. And then rank 2, rank 3, rank 4, and rank 5 you can't have, right? So you can't have rank 5 if you have all 5 eigenvalue 0. Even if you have one eigenvalue as 0, you cannot have full rank, right? So that's a property we have seen. So up to rank 4 you can go, and then you will have your geometric multiplicity. It's very easy to cook up those examples there. Now a challenge is to find such matrices where all entries are non-zero. Not all entries, why not? All entries are non-zero, right? So this is a bit of a challenge. I'll let you think about it. Can you possibly do it is an interesting question to ponder. Okay, so with this, we'll stop this lecture. Thank you very much.